Oh, hi there. You scared the crap out of me. Guess I got no choice but to teach you about the right-hand rule, huh?
Let's say I've got a particle with a charge plus 2 coulombs, and it's zipping through a magnetic field at 4 meters per second. I guess I shouldn't say zipping. That's not all that fast. Meanwhile, it goes through a magnetic field that has a strength of 3 Tesla. So I want to know what magnitude of force the particle feels, and I want to know what direction it feels that force. Well, anytime a charged particle goes through a magnetic field, it experiences what's called a vector cross product. As a reminder from earlier in the year, these little rightward arrows do not mean the vector is pointing to the right. It literally just means, hey, this symbol that I'm above is a vector. Now, ultimately what I'm solving for is the force. Now, force, like any other vector, has a magnitude and it has a direction. To find the magnitude, I'm just going to take the magnitude of the velocity, the magnitude of the magnetic field, multiply those together, multiply it by the value of the charge, and then multiply the whole thing by the sine of the angle between the magnetic field and the velocity. So what's that angle going to be in this example? Well, let me draw those vectors real quick. My velocity, that was ugly. My velocity vector is heading to the left, and my magnetic field vector is pointing downward. So just from looking at this picture, you can see that the angle between them is 90 degrees. So I've replaced theta with 90 degrees. And hey, the sine of 90 degrees is just 1. So now it's going to be the value of q times the value of v times the value of b times 1. So let me plug those values in. It was a 2 coulomb charge, it was 4 meters per second, and it was a 3 Tesla field. That means it's going to feel a magnitude of force of 24 newtons. Now I need to figure out the direction. And to get the direction, I'm going to have to use the right-hand rule. For me to demonstrate this, you're actually going to have to see my right hand, which means I think we need to approach this first-person video game style.
Uh-oh. A wild magnetic field has appeared, and it's pointing downward. Here comes a particle zipping to the left, so I'm going to karate chop in the direction of the velocity, that's to the left, and then I'm going to rotate my palm until I can point these fingers downward. So my index finger is the velocity vector. These fingers here are pointing downward, that's in the direction of the magnetic field, and my thumb will tell me the direction the particle feels a force, which is, oh crap, it's feeling a force directly toward me. Dodge!
So ultimately what we've discovered through this harrowing journey is that the particle is feeling a force out of the screen toward me. And the way that I would draw that vector is this. It is experiencing a force out of the screen. All right, y'all have a great day.